Well, thank you. It's a pleasure to be here with you today, and I'm grateful for the privilege. As you heard, I'm going to talk about rigor, reproducibility, and transparency paths forward. Here's my disclosure slide. On the right, you see people who have helped me with various ideas that I'll be presenting, and perhaps the most important thing here is there's my email address, so if you want these slides and you want to look at them more closely, just send me an email. An outline of what I'm going to talk about is as follows. I'm going to start very, very briefly with a taxonomy of the way research goes astray. I'm going to give a few examples that I think are enlightening. I'm going to then talk about focusing on the essence of science, which several of the prior speakers have emphasized. And then I'm going to talk very briefly about concrete ways to move from recognition of some of these challenges we face to mitigation of straying from good science. So here's my very broad taxonomy of how things can go wrong. There's fraud, there's distortion, and there's gross error. What's important to realize, I think, is that these are not new events. These have been happening since the history of science. We hope that fraud is rare, but it does happen. There's actually quite substantial evidence that Gregor Mendel cooked the books a little bit on his P's. This was demonstrated by Sir Ronald Fisher, who showed that the frequencies in the Punnett squares of his 2x2 tables were far too close to the expectations to have occurred by chance. Moreover, at certain points, the second law of independent assortment specifies that genes sort independently, and he was able to show that this was the case, which of course would not be the case if the genes were linked. So he had been studying 7 unlinked genes. The probability of, by chance, getting 7 unlinked genes in a genome the size of the P genome is effectively 0 to do it by chance. So clearly Mendel was playing with the data a little bit. Distortion. This is Einstein sitting with Lord Eddington. There's a very famous story after Lord Eddington had shown that rays of light appeared to bend toward the sun due to the sun's gravity, thereby confirming part of Einstein's theories. And a reporter asked Einstein, what do you think, what would you have thought, Professor Einstein, if Lord Eddington had not confirmed your result? And Einstein replied, I would have felt very bad for the good Lord because that meant the experiment would have been wrong. Einstein was quite confident his theory was correct. It was correct. But what Eddington had to do to actually get the data to conform and show it was correct was throw out a few outliers because some of the measurements weren't so good. Probably was the right thing to do. He did throw out the outliers. He did get the right answer. We know in history it was the right answer. But there's a little bit of that bending of the truth, perhaps, that distorting. This is not new. And then there's just gross error. Some of you may have heard of N-rays. If those of you have not heard of N-rays, the reason probably is because N-rays don't exist. But Professor Blanlon, back in the last century, thought that, in fact, he had discovered N-rays. N was for Nancy, the town in France where he believed he had discovered them. And these were widely being studied in his lab and elsewhere. And Robert Wood from Hopkins was a physicist and a little bit of a trickster, kind of was skeptical of this, flew over to France, stopped in to see Professor Blanlon. And the way these rays worked and were demonstrated is that they were detected by a calcium sulfide thread that glowed slightly in the dark when the rays were refracted through a 60-degree prism of aluminum. And so Robert Wood went in, and the professor showed him this, and then he said, Professor, what is that over there? And he sort of reached into the machine and palmed the prism and put it in his pocket. And he said, Professor, could you show me again the N-rays? Sure. He turns on the machine. It's there. You see, there they are. But of course, the whole prism that's supposed to make them work is gone, and so the whole thing fell apart. There's no evidence that Blanlon was cheating. As far as everybody can tell, he just had deceived himself. He was confused, and he probably didn't have rigorous controls in to help him understand what was going on. Robert Wood put in a very simple control. Take the prism out that you think is the vital key and see if you still get the observation. All right, let's go to a few more modern examples of specific instances where these things go astray. So this is a paper that came out about 1.5 years ago. Some colleagues and I saw it, and I started to be interested in it, and I read a little bit of the paper, and it showed that some calculations that if you put in a policy that got the the amount of calories in kids' meals to go down a little bit, that you by about 132 calories per week, given how often the average kid ate at fast food, and you multiplied those calories out over 52 weeks in a year, that in fact the average kid would gain 2 less pounds per year as a result of this policy. I thought, that struck me as slightly ambitious, but well, maybe it's possible. But then I read further, and it talked about calculations include children who are estimated to eat fast food 4 or more times per day, every day a week. So 28 meals per week in fast food. Right off the bat, that just started sounding hard to believe. And then if this law were passed, for these kids, you would see 27 fewer pounds per year of weight gain. And that really struck me as implausible. I thought, anybody who's ever been a kid, had a kid, seen a kid, not kidding, you got to think this is a little questionable. So I called up Kevin Hall at NIH, and I said, Kevin, you've got this new model, this mathematical model you published on predicting kid weight gain as a function of calories. Can you give me from your model, what's the estimate of this? And he said, yeah, I come up with an estimate of about 0.5 kilograms of excess weight by increasing daily intake by 19 kilocalories per day, which is 132 kilocalories in a week. And that's from age 7 to age 12 years, so it's a much longer period of time. That's not just these numbers here that the author gave her for 1 year. So basically the authors were off by easily an order of magnitude. And the further you went out of time, the more orders of magnitude they were off. So we wrote a letter to the editor, and I was very surprised. I thought we'd get sort of a sort of sheepish apology from the authors who had corrected in the literature and so on. And they actually just retracted the paper, which, they did apologize. They did point out the correction. They acknowledged that our calculations were accurate. But I was impressed by their integrity of retracting the paper. And it was clear to me they weren't trying to make a mistake. They just hadn't thought about the mathematics of it. Math seems to be both a common problem and a common solution to many of these things. This is another paper we came across, or is our letter to the editor about another paper we came across. And this came out, not in perhaps a journal many of you publish in, the World Journal of Acupuncture and Muxobustion. And a paper came out with a randomized controlled trial showing that meridian massage caused weight loss. And in fact, in people who started at baseline of about 75 kilograms, and just to give you a sense, I'm about 75 kilograms, they lost close to 10% of their body weight as a result of massage in 8 weeks. And while that sounds terrific, it almost sounded a little too good to be true. It's hard, even with the best pharmaceuticals, to get people to lose 10% of their body weight in 8 weeks. And so we looked a little closer, and they reported the baseline BMI, and then the follow-up BMI, and the baseline weight, and the follow-up weight. And you quickly realize if you do a little work, since BMI is weight over height squared, then if you know 2, you can solve for the third. Now, when you're dealing with ratios of means as opposed to means of ratios, those are not always the same thing. So we had to use some geometric mean approximations. I won't bore you with all the statistics, but we did a little math, and we were able to show that in order for this to be true, that the average person would have needed to gain about 6 centimeters in height during the course of the study in order for these results to be mathematically possible. So we wrote to the authors who didn't respond. We prompted them again. They didn't respond. We wrote to the editor. Finally, after a long wait, the editor extracted from them the fact that they had made some error. We never understood the nature of the error. It was never specified. But in fact, then they published a fresh table of results in which the results were only half as much weight loss occurred and were now mathematically possible. Cluster randomized trials are another area where we see lots of mistakes, and these have become more popular. Cluster randomized trials are trials in which you don't randomly assign individuals, for example, individual patients, to treatment or control, let's say, but you assign classrooms all at once. This entire classroom will get treatment. This entire classroom will get control, or this entire school, or this city, or this restaurant, or this work site. When you randomize the whole cluster, that's a cluster randomized trial. Thinking about what Dr. Lynch spoke about earlier, this is not just unique to human clinical trials, but we see this a lot with animal studies. So people assign an entire cage to get diet A versus diet B, or an entire litter of mice to get diet A versus diet B. And when I talk to people who run basic mouse studies, and really top people, and I say, by the way, do you ever, keep multiple animals in the same cage and sign the whole cage size? Oh yeah, sure. And I say, how do you take the clustering into account in your statistics? And they say, clustering into account in the statistics? And just blank. And so, okay, why don't you give us a call? Maybe next time you're analyzing the data, we could try to help you out. So this is something that's very widely confused, because if you don't take that clustering into account, you can radically misestimate the statistical significance of the results. You can radically misestimate your standard errors. People are so confused about it that even methodologists who write about it sometimes get it wrong. And this is an interesting sort of story about when should a paper be retracted. So this paper came out in a journal called Obesity Facts, and it was from some epidemiologists. They were writing about how to do cluster randomized trials and biases that could occur. And as I started reading it, I started coming across statements that I was pretty sure were not only factually incorrect, but were knowably factually incorrect based on first principles a priori. That is, you didn't need to do a meta-analysis, you didn't need to do a simulation. These were mathematically, verifiably incorrect statements. And so I showed it to some of my colleagues who are experts in the statistics in this area, and they said, yes, you are right, these are not correct statements. So we wrote a commentary to the journal. The journal had another statistician independently review it, who we didn't know. That statistician concurred with us. The editor then wrote to the authors and said, we really would like you to retract this paper given the situation. The authors said, no, we refuse to retract the paper. And so the editor then issued a commentary of his own along with ours, in which he described this whole story, and it's all sort of listed here. So letting the reader beware, but the original paper then still stands. So people can still read the original unretracted paper, which has sort of no mark on it indicating that it's wrong, and get the wrong information. This has led me to propose a lyrical change to one of our classic tenets of I can't get no satisfaction, I can't get no girl reaction, from Mick Jagger and Keith Richards, to I can't get no satisfaction, I can't get no editor retraction. We then followed this up with writing multiple letters about many of these things. We've gotten a fair number of papers retracted, but we've had all kinds of interesting experiences in trying to correct some of the literature. And these are things where, for example, some journals will want to charge us a fee, have demanded that we pay a fee to publish our letter to the editor correcting the error in a paper they've published. Or saying that we have to sign a paper that if there's anything wrong in our paper, there's a $10,000 payment will be required if we have to retract it. And you can understand the disincentive this provides to the honest person who says, you know what, I made a mistake. I want to retract my paper. Well, then for this one publisher, you owe them $10,000. We have editors who just would never respond, as you saw before, one editor who wouldn't retract. And so we published a commentary in Nature in which we described all this, and you can see, and that's got a fair bit of attention, and I think that's actually already causing at least one major publisher to alter their policies on charging authors to submit letters to the editor that correct papers. What's the way forward on this? Well, I think the way forward is to really focus on the essence of science. And here I'm very much, I think, building on what Dr. Myers said and what Arya Sharma said, is that we can't look into the souls of people. We don't know who's a truth teller and who's not a truth teller. And even if people are honest and good, that doesn't mean they don't make mistakes. What we can do is look to the science, right? And so we like to say in our group, in science, three things matter: the data, the methods used to collect or produce the data, which give those data their evidential meaning, and the logic by which the data are connected to conclusions. And that's it. Everything else is a distraction. And so if we want to improve the science, we need to focus right there. And so that's what we try to do when we're thinking about how can we take these sort of rigor and reproducibility enjoinders from the NIH and turn them into concrete ways to mitigate this kind of straying from good science. One we really think is important is data sharing. And I wanted to put this one up because, you know, I've made some fun of other people's mistakes. Well, we make mistakes too. In fact, I catch mistakes in our group all the time, which of course makes me worry about the mistakes I don't catch. But hopefully we've caught most of them before they go out for publication. This is one we didn't catch before it went out for publication. So we published a paper. In this case, it was on the NHANES data, which are publicly available sort of a priori. And we used some equations that were in another paper someone else had published. That author was skeptical of our results, tried to reproduce them in the public data and could not reproduce them. Wrote to us, said, I can't reproduce your results. We went and checked, and we said, oops, you're right, we made a mistake. We then went and said, part of the reason we made a mistake is there's a mistake in your paper too with the original equations. So we all got together and we had a little love fest and we published this commentary correcting the errors in both papers. But we could only get to that point because the raw data were available. It allowed that other author to go back and check what we did. And so as much as we didn't enjoy finding that there was a mistake in our paper, we were able to correct it and do the right thing and help that the raw data were available. I think checklists are very valuable. This is from another paper that we found a mistake in. This was from a meta-analysis of glucomannan that showed it was effective for weight loss. Oh, I'm sorry, I've jumped the gun here. This is a different thing. This is from Retraction Watch showing that a paper had to be retracted because the authors inadvertently uploaded and analyzed the wrong data set. They analyzed one of their older data sets from a different study instead of from the current study they were trying to publish. They then published on the wrong data set. You can imagine how embarrassing and terrible this is. They had to retract it, but we could all, imagine doing something like this if we don't have good practices. That's why surgeons use checklists. That's why the pilot uses checklists when he or she takes the plane off. It's too important to make a mistake. We need checklists. And so I think we're trying to work on developing one for use in our group, and I think as a field we need to start doing this. There's the value of public information perspective. The value of information perspective is that not all information is equally valuable. One of the questions I don't think we've asked as a field is, do we want all studies to be subject to the same level of rigor? And in fact, one of the complaints we sometimes hear of people with rigor say, this is going to make all studies more expensive. We're just going to do less research if I have to spend more money having more people do more checking. I think that's right. There are some studies that are just not that important. Maybe because it's a real quick exploratory one that's funded by the internal pilot mechanism, or maybe because it's sort of just a cute little study. There was a study, I kid you not, this is a true study, that somebody published showing that male but not female drivers were more likely to stop and pick up a female hitchhiker when she had larger than smaller breasts. This is a true study, and you're left to wonder, was that really that important a use of, research funds and resources? Probably not, and probably we didn't need a lot of extra rigor on that study. But some of the studies that Arya Sharma talked about, when you talk about a drug being pulled from the market, you want a lot of rigor. And so I think we want to see if we can calibrate that. But I think the key is we should not have variation in rigor in reporting. So that my feeling is you can be as sloppy as you want in science, but just tell the reader how sloppy you are. So if you've not checked things, let them know. If your data are not publicly available to be checked, then people should know that. All right? If you haven't had a professional statistician look at this, so that's where good reporting comes in. I think we can't compromise that because then people can be their own judge of how good that science is. All right. We know that methodologic training is important. This is from a meta-analysis we helped some people correct. They initially got a significant effect of glucomannan on weight loss. We found that they didn't know how to calculate standard deviations properly. They had gotten actually a negative standard deviation, which since it's a square root of a squared number, unless you're dealing with, imaginary numbers, you can't have a negative standard deviation. We helped them correct this. They didn't want to make this mistake. They didn't have the statistical training. We need more statistical training out there. We try to give some of that. NIH has funded us to do these short courses. We invite any of you to come. The next ones are happening at UAB this summer. We talk about mathematics and causal inference in obesity research. And lastly, I really think that we need to up the value of the culture of truthfulness. One of the things I'm intrigued by is the Robert Wood Johnson Foundation's idea of a culture of health. That's their new mission. I want to build a culture of health. And I think that's great, but we better in science have along with it a culture of truthfulness. This is a thing I realize it's hard to see. This is a headline from a press release affiliated with the CDC in which they talk about this new alliance for a school-based program and how well it's working, and we've delivered on the promise to help reduce childhood obesity. And then when you go back to the actual study, you get statements like, analyses showed no difference between healthy school program schools and control schools in overweight or obesity programs. How in heaven's name do you get from that finding to a positive press release saying we're delivering on the promise to reduce childhood obesity. I don't think that speaks to a culture of truthfulness, and I think that's what we need along with our culture of health. This is, I wanted to show a positive example from this investigator. I don't know these investigators who did a randomized controlled trial of capsaicin. They hypothesized it would produce weight loss. They found it did not, and they have a simple statement. No significant interactions between supplement tests were noted for any common variable. These results suggest that the acute ingestion of 500 milligrams of capsaicin is not effective. Just speak the truth, say it. We're having a Sackler Colloquium at the National Academy of Sciences. It's open to the public. You can find out more on the National Academy of Sciences website. I have the privilege of being one of the organizers of it. We'll be going over these ideas in detail and talk about how for science as a whole, because this goes beyond nutrition, we can try to increase the rigor and reproducibility and transparency. Thank you very much.